Okay, so let's keep going with our review, which will be done very soon, by the way. So now we're looking at section 4.3. Let's get this open. And we're looking at Riemann sums and definite integrals. Okay, so this is where they're first introducing the notion of definite integrals to distinguish them from indefinite integrals. These are the ones where we will evaluate an integral over a specific range of values. Okay, so now, up to this point, we've been trying to calculate the area under a curve using rectangles, and so far it's worked pretty well. But one thing that we did make sure in those cases was that the rectangles all had the same base. Now, here we're going to try something a little bit different. We're going to use something called Riemann sums, where the rectangles themselves don't necessarily all have the same width or base. It can change. And you can see in this diagram, that's exactly what's happening. They start out very skinny, and then as we move along, um, they do get a little bit wider, although there's a specific pattern to the way they're getting wider. It's not just completely random. And like here, you can see there's a formula that's telling us how to determine the endpoints for these growing rectangles. Okay, so they want us to start with the case of f of x equals the square root of x. Okay, so let's see how that works out. All right, so the function we're interested in is square root of x, which starts at 0, 0, of course, and then the curve actually increases at a progressively decreasing rate. And you can see, so they're interested in the area between just 0 and 1. Okay. All right, so it looks like we've got one, two, three, four rectangles. And now C. So by the way, if you remember this formula, what this is telling us is the sum of the areas of these rectangles. And the fact that it's a limit is there because of the fact that we want to do this in such a way that the number of rectangles approaches infinity. Because we know that if we don't have enough rectangles, this approximation that we're trying to do is not going to work terribly well. Like here, for example, you can see clearly that these rectangles are too tall, and the area under these rectangles is quite a bit larger than the actual curve itself. But that problem would take care of itself if we had enough rectangles. So we're going to take the limit of this process as n goes to infinity, which means the number of rectangles is going to infinity. And in each case, for each rectangle, we have whatever C is. Now, C could be any part of this rectangle. It could be the left end point, it could be the right end point, it could be the center or midpoint. It could be anywhere in this rectangle. So f of C, and by the way, it doesn't really matter where because as far as the height of the rectangle goes, the top of it is a flat line. So any point inside this interval will do the job. This is the height of the rectangle. And then depending on the size of the width or the base, that would be our delta x. Now here, if you notice, for the first time, delta x has an index. And that's because with Riemann sums, we're not assuming that all the rectangles have the same base. So in other words, it's not a constant any longer. So we have to have that subscript there. So this entire expression is the area of rectangle I. And so there are n of them that we add up, but if we only have a small number of rectangles, as we've seen, the total area of those rectangles is likely to be significantly different than the actual area under that curve. So that's what this is doing here. As we increase the number of rectangles, we're getting closer and closer and closer to the true area under this curve. Okay, so that's the setup. Now here they would like us to use, oh, by the way, they're using this key term here, partition. That essentially refers to the way the area under this curve is being approximated with triangles. So in other words, this is the method for subdividing the area of interest. In this particular case, into rectangles. It doesn't have the word partition could apply to anything, but we're taking some area and breaking it up into pieces. That's essentially what we're doing. So we're dividing the area of interest into rectangles, and we can do this in many different ways. Each time we choose a different number of rectangles, we're going to have a different partition. Okay, so the partition refers to the way we've subdivided that area under the curve into rectangles. So you're seeing one right there. So they want us to define the partition as CI. And again, because the widths can be different, we need to do this for every single one of those rectangles. I squared over n squared. Okay. So in other words, actually, let me copy this into my notes so you can see it better. Okay, so that's our formula. CI, once again, let me copy it down here. CI, I squared over n squared. So this would be C1, C2, and this is C n minus 1, Cn. Okay. All right. So now, of course, Cn by definition would be n squared over n squared, which is 1 because of the way it was defined. So in each case, we've got the subscript here squared divided by n squared. Okay. So in other words, this formula for the partition, meaning how it tells me how to break it up into pieces. Okay. Now, if they were all the same, like in the previous sections, then we wouldn't even need a subscript. It's just always the same. Okay, so this is what we have. Now, the widths between these endpoints, delta xi. All right, so for example, this first rectangle is C2 minus C1. Okay, delta x2 would be C3 minus C2, et cetera, et cetera. Okay. All right, now, what does this get us? Well, in general, the left endpoint of the ith interval or rectangle is I minus 1 squared over n squared. Okay. And so, therefore, I minus 1 squared over n squared. And so, for example, rectangle 1 has a left endpoint of 1 minus 1 squared over n squared, which is 0. Okay, so that is here. Think of that as C0, the starting point. And then um, the next rectangle, rectangle 2, has a left endpoint of 2 minus 1 squared over n squared. And that's exactly what you're seeing here. Okay, so the first rectangle is, you can barely see it. It's so small. Right here, there's a teeny tiny little rectangle. It starts at 0 and goes over to 1 over n squared. Okay, and then from that point on, just by looking at the graph, you can see the endpoints. But in general, it's nice to have a formula like this. Now, what they're telling us here is that that implies that the width of a given rectangle, or we'll call it rectangle I, can be written, and you can see that these are in fact two consecutive endpoints. Um, so for any two consecutive endpoints, the gap is equal to I squared over, whoops, n squared minus I minus 1 squared over n squared. Now, what they're going to do is they have already, well, done it for us, um, expanded this. And, if you want to work through all the steps, and if you want, you can apply FOIL here. F, of course, would give us I squared. O is negative I. I is also negative I. And then last is positive 1. So, but remember, we're subtracting that. So this expression can be rewritten as and then we can simplify it as much as we want to. So, of course, these two drop out, and we're left with 2I minus 1 over n squared. Each delta x rather, equals this expression. All right. Now, with all that being said, yeah, this is what they're going to do. Now, remember, this is what we're trying to solve for. The sum of all the rectangles as n goes to infinity. Now, this particular function, f of ci, meaning the height, is here. It's the square root of I squared over n, because now remember, ci itself, which we define way, way back here, is I squared over n squared. but the function itself is radical x. So therefore, f of c of I must be the square root of I squared over n squared. That's this piece. And then this piece, which we just figured out ourselves, is the delta xi. Okay. So what they're going to do now is go through a bunch of algebra, but they're going to do more than that. If you remember last time, we had these wonderful formulas. Let me just remind you what they look like. They're yeah, these can be very, very helpful. The sum of the first consecutive n i's is, okay? And then we do the same thing for the I squared. We have, oh, this one's a little bit messier. N plus 1, 2n plus 1, all over 6. Now we're going to need that. As you can see, now we're not going to necessarily have to go through all these steps, but you see what they've done. They rewrote this as I over n cubed because it's a constant. And here under the summation sign, we have 2i squared minus I. Um, Now the 2 is being multiplied here. This is I squared, and this is I. And so then we do a little more algebra. Now, when we get to this point, we can simplify. 4n cubed over 6n cubed is 4 over 6. Then we'll have 3 over 6n. Then we'll have minus 1 over 6n squared. Now, the important thing here is that when you take the limit like this, when you have n in the denominator, both of these go to 0. So you're left with 4/6, which is, of course, 2/3. Okay? So after all that work, we discover that the area under this curve between 0 and 1 is 2/3. Using the limit definition with what we call Riemann sums. Okay. Well, um, oops, hold on. I'm going the wrong way. Now, of course, we know the rules of integration. We don't need to go through all these steps. If you wanted to do this, um, what you would do instead, if you're not going to use the limit rule, the limit approach, is you would take this function and you integrate it over the range from 0 to 1. Now, we're going to get into this in the next section, but this is known as a definite integral. And so what we have to do is this. So first things first, let's rewrite radical x as x to the 1/2. And we end up with x to the 3/2 over 3/2. And instead of having a constant here, like we would with an indefinite integral, we have to evaluate this over the range from 0 to 1. Okay. Now, first things first, let's clean it up a bit. And we can factor out this 2/3. And just remember, when we say evaluate, what you're actually doing is this. You're evaluating this function first at x equals 1 and then x equals 0 and subtracting. But you can see this is nothing but 2/3 times 1 minus 0, 2/3 times 1, 2/3. Okay, now they're going to, in a few slides, they're going to show us the formal definition of a definite integral. But in a nutshell, this is what you do. You evaluate it the normal way, and then you apply the two endpoints, the upper and lower limits of integration, to come up with your answer. And that answer corresponds to the area under this function between those two endpoints that you chose. Okay, so yeah, so let's see. Okay, here we go. By the way, they introduced this notation along the way, because in the Riemann integrals, sums rather, the differences or the bases of the rectangles are all different. What they've introduced is this new notation. So remember, we had this case. We have a curve, and we introduce all these rectangles, and each one is getting progressively wider. So what they've done is they introduced this notation. That's the double bars can mean different things in different contexts. Here they're using this to define what they're going to call the norm of the partition. And all it means is the largest, or I should say the width of the largest rectangle in the partition. So in other words, if we take the limit as the norm goes to 0, that guarantees that all the smaller rectangles will also go to 0. That's why they're doing it this way. So if you notice the statement here, um, we've got the limit, not as n goes to infinity, but this norm goes to infinity because we're applying this to Riemann integrals rather than, or sums, rather than the ones with the same, where the rectangles are all the same. Okay, so this is a more general approach to doing this. So again, this represents the area of rectangle I, and we're adding them all up. We're taking the limit, okay, and then this has some value L, we'll just call it. And then assuming that the limit exists, which is what this is for, we can make the following claim. And so we have an integral over a given interval for the function we specified. And this is what we mean by a definite integral. And of course, this is assuming that we've chosen a function and we're only interested in analyzing it over a closed interval a to b. So this in turn equals the area in this shaded region. Okay. Now, luckily, though, we don't have to learn a bunch of new rules to do this. They're just the standard integral rules, but where we evaluate the function of the two endpoints and subtract one from the other. That's the big difference. Okay. Um, like here's one. Now, they're going to go through all the limit definition. They're going to come up with -3. Let's see if we can do this with the rules. We'll see how it compares. Um, the function is just simply 2x dx. There's a graph in here somewhere too. Yeah, all these rectangles. As we take the limit of the uh, width of these rectangles, we end up with we should end up with the correct solution. And so how would that work with the rules of integration? First thing we'll do is factor out this constant. And if you remember, the power rule of integration is for an indefinite integral, we need the constant. Here we will not need that. What we have instead is x. Now remember, x, there's an implicit exponent of 1 here. So actually, well, let me write it a little differently. When you have the actual integral, we usually change the notation slightly. So in other words, it ends up looking like this. And every book is slightly different, but most books write it like this. And what this is telling me is that now, of course, these two cancel each other out. I'm evaluating at 1, subtracting -2 squared, and I end up with -3. Okay, now they got the same thing. Now you're probably wondering, well, wait a minute, -3. The reason why it's negative is because if you notice, this area here, using the rule we just defined, will have a negative area, so to speak, well, or at least a negative integral, and this will be positive, but because this is clearly larger than this, between the two of them, the total will be negative. Now, what they're making the point here too that when this happens, we cannot interpret this as the area um, because on the left we clearly have a negative. We're under the horizontal axis, but it does represent the integral. So yeah, when we have functions that are underneath the horizontal axis, we have to do something a little different to solve for the area. Anyway, so this is the general approach now to finding the area under a curve between 2 points. We'll write it like this. And, nobody says you have to use the limit approach. As you can see, it's a very, very messy approach. And it leans very heavily on those definitions we had, the sum of the i's, the sum of the I squares. But instead, since we've already been exposed to integration, we're going to stick with the rules that we know. Okay. By the way, here, because we're entirely above the horizontal axis, this integral can be interpreted as the area under the curve. All right, so here's an interesting one. 4x minus x squared. It's an upside down parabola. And we're interested in the area between 0 and 4. All right, f of x equals 4x minus x squared. So how do we figure this out? We have an integral defined between 0 and 4. So we can break this up into two pieces. Then we apply the power rule. Okay, now we can maybe do a little algebra here. 4 divided by 2, we can write this as 2. Over here, we can move out the 1/3. Not that it's not absolutely necessary. It might just be cleaner that way. All right. Now, if we want to combine these, we need a common denominator. And we ultimately end up with 32/3. All right. A little quicker than the limit definition, I think you'll agree. There's a few more examples here. Maybe we'll take a look at these. No, I guess, no, I think that example is enough. Let's move on to this. Um, no, all right, what the heck? Yeah, no, that's right. We can move on to something else. What I do want you to see now, by the way, unfortunately, there's a typo in here. There's some very important results that we need to know when dealing with definite integrals. As a starter, imagine if the range of values here was a and a. Well, that by definition is equal to 0. Okay. Because what you're effectively doing then is you're taking the area of a straight line. If you remember from your travels, the width of a line is defined to be 0. So therefore, this is 0. And then now this one, if you change the limits of integration, then you get a negative result. So getting back to this example here, if you really need this area, remember how we did this. We have -2 to 1. What you would have to do is, instead of integrating this function from -2 to 1, you break it up into two pieces. But in order to avoid having a negative area, the one on the left could be rewritten as, um, and that guarantees you'll get a positive value. And now you can interpret this as the area of the two sections, which we can then add together. Okay. All right. What else? What other properties do we need to know? Wow, that one turned out to be a trapezoid. Huh, look at that. All right, let's try this one because it will provide us with a negative result. I think they want us to see that. 3 to 0, x plus 2 dx. All right. So using the power rule, here's what we have. Now we can evaluate it. Yeah, we can move this half out here. Okay. Well, sorry, I meant to rewrite that as 12/6. Um, uh, what am I saying? 12 halves. Negative 21 halves. But if I changed the limits of integration to 0 up to 3 of the same function, x plus 2 dx, I'll end up with um, and then I'll factor out this 1/2, although it's not absolutely necessary. I find it's simpler that way. And now when you evaluate it, you'll see that why, what do you know? We are going to get positive numbers. And there it is. Okay. Now, here's an interesting result. If there's a really good reason for it, like especially when you've got a function like we just saw before, where some of it is under the horizontal axis and some of it is above, you can take this function and rewrite it in a more convenient form. Just in other words, you're splitting it up. You notice that C, we just introduced that here. But the two will add up to each other. Okay. So this might be helpful when you're breaking up a problem into two parts. Maybe the behavior of the function is very different on either side of C, like maybe being negative. Okay. And that's what that's for. It's really just for our convenience. Oh, here's a good example of that absolute value. Perfect example, because as you know, absolute value is a piecewise function. Its behavior is very, very different on either side of the vertical axis. In fact, it can be formally written in it like this. Because if x is positive, it stays positive. If x is negative, we multiply it by -1 and it becomes positive. So the integral of this between, let's say, -1 and 1, I think you would find that taking the integral of absolute x would be a nightmare. So what they're suggesting that you do, say, all right, don't worry about it. From 0 to 1, we just simply have negative x. And from, whoops, sorry, 1 to 0, I should have said, um, the function is actually just negative x. And then from 0 to 1, it's positive x. Okay. So whatever that turns out to be, let's see what we get. Let's see. So what do we have here? 1/2 minus 0. All right. Now, of course, this one has a negative. So this is 1/2 plus 1/2, which is 1. And so what you effectively have just done, let me just move this for a second. It's figured out this area. Okay. And on either side, we have an area of 1/2, um, which you could tell with geometry if you were so inclined. All right, here's why. This is just 1. Okay, and this is 1. So this is a triangle. Remember, the area of a triangle is 1/2 base times height. So the base is 1, and so is the height. So for each one, we have a triangle with an area of 1/2 times 1 times 1, a half plus a half, which is 1. So in this case, we were able to do it with geometry because it's a very simple function. With most cases, of course, you've got to use integration. Otherwise, you'd be here all day. Okay, so now what comes next? Oh, properties of definite integral, these just perfectly parallel the ones for um, indefinite integrals. You'll recognize all of these from a previous chapter. Um, let's see what examples they have for us. Now here they're being very helpful. They're showing us some of the parts. We don't need that. We can do this. Let's try these. We don't need any help at all. Let's try this. Remember, when you're taking the integral of a polynomial like this, that would be the power rule for integrals. And so this is going to give us okay. Now this first one is just going to be negative x cubed over 3. And in each case, we're evaluating it from 1 to 3. Now the integral of dx is just x. All right, so let's see what we have. Oops, sorry, that's 1 cubed. And we got to watch out for those, all these negatives. As a matter of fact, you know what I'm going to do here? I'm going to actually simplify this rather than diving right into this. Let me simplify it again because you know what's going to happen. There's such a huge risk of making a sign error. Let's do this instead. Same thing here with the 4 and the 2 and the 3. I think you'll agree that'll make it less likely that it will make a mistake. So we have 3 cubed over 3 minus 1 cubed over 3. X cubed, sorry, x squared, but that's 3. So let's change that to 3 squared. So it's just direct substitution. Okay, what do we have? All right, here we go. So here we have 2 times 8, which is 16. Then we subtract 6. So of course we'll need a common denominator. We can rewrite that as 30 thirds. And we ultimately end up with 4 thirds. Okay, there we go. Beautiful. Okay, now let's see. We don't need to do every single one of these examples. Let's see what's next. Oh, okay. That was 4-3. Okay. So 4-4, let's take a peek at what's coming up in 4-4. Um, oh my God. The fundamental theorem of calculus. This is really what you're going to see here is really why all of this is so important. And you can see they mention here that it was discovered independently by Newton and Leibniz, as I've already mentioned. Newton and Leibniz were the two who are um, formally defined or credited as being the founders of calculus. And so, what are they trying to do? Well, this is what justifies what we've been doing all this time, which is to say, when I take an integral, a definite integral, like here, what is it that lets me evaluate the integral? And then this part is what the fundamental theorem of calculus is explaining how this part works. So they're writing it in a very interesting way. All right, let's get this here. Now remember the way the notation works is this is an antiderivative or integral of f of x. In other words, what this is saying is once you've integrated this function, you notice how what they're doing here, if you write it the way we've been using it, I've been using this notation, but you can see it's the same thing as this. You're evaluating the integral or antiderivative twice, once with b, once with a, and then you're subtracting. And that is what we mean by a definite integral. Okay. Now, of course, if Newton and Leibniz think that this is valid, then that means we're okay using it. Okay. So, in other words, we've been using it up to this point, but this is what formally defines the fundamental theorem of calculus is what justifies our ability to do this. Okay. So, that's what this means. This is where the idea of definite integration comes from. Let's see. All right. So let's do one more example. We don't need to do every single one of them. Let's try this one. Okay. So we first break it up into pieces. Okay. And using the power rule for integration, if it's a definite integral, then we need a constant. If it's uh, I'm sorry, an indefinite integral, if it's a definite integral, then we can evaluate it ourselves as we're seeing here. So we're going to have, okay. So, by the way, I just want to mention here that f of x equals x squared minus 3. Capital F of x is x cubed over 3 um, minus 3x. Okay, if you were to take the derivative of this expression, you would see that it equals what we have on the left. Okay, so the derivative gives us this. That's how they're related to each other. Oops, okay. Anyway, so we can just carry on from here. We'll rewrite this a little more simply. We have, for example, here um, x cubed from 1 to 2, and then we subtracted 3 x 1 to 2, and then we have 8 minus 1. Oops, sorry, that's positive 1. 1/3 of 7 minus 3. So we'll rewrite this as 7/3 minus 9/3, and we end up with negative 2/3. Okay. And then we can do all the others too if you want. So now I guess we're probably going to have to leave it right here because we're going to introduce this very important extension of the mean value theorem that specifically applies to integrals. Um, well, you'll see, but we're going to use it for is something very important called the average value of a function. And by the way, there's two parts to this fundamental theorem of calculus. The one that we're very familiar with is the one we just looked at. This is the other part of it, basically. We don't use this nearly as often, but it's important to be comfortable with it. So I think we can basically stop right here for now. And I think, let's see, what else do we have to do before we're ready for the, by the way, chapter 7. It's a good thing we're doing all this because chapter 7 is just a bunch of applications of integration. So by going through all of this again, it'll be very fresh in our memories when we get started with applications of integration, which is chapter 7. So this part is almost done. I think there's only one more section left, but we're close. We're close. We may wrap it up next time, and then we can finally do some new content. Okay. But for now, we'll stop right here. Next time, we'll dive back into this, the mean value theorem for integrals, and which is based on the mean value theorem that you saw in Calc 1. And then we'll take it from there. Okay. So I'll see you next time.